know if there was a deck, you've got a laptop.
I think it was it G-Champs?
Okay.
You want to test out the clicker?
There we go.
All right then. Good morning, everyone. We are the Smart Drip Irrigation System team. I'm the team lead, Adriana Lopez, and these are my team members, Maggie.
Rubina, Martin, and Brian.
And we are super grateful and honored to be presenting today to the IAB. Our customer is John Weiss. He is with Bionica, which is a nonprofit agricultural organization in Nicaragua. Our advisor is Dr. Trompetta, who is with University of Houston, and our mentor is Dr. Varela. So let's get started. So here's our agenda for today. First, we're going to go through an overview of our project. Then we're going to head to the specifications, functionality, prototype demo, and then our conclusion. So for the overview, here is a bit of a background. So Nicaragua is a Latin American country that suffers from a lot of external and really sporadic weather patterns. So they regularly experience droughts, tropical storms, and this has led for the population to really suffer in regards to their agricultural products. Specifically, 18% of the population in Nicaragua is severely undernourished because of this. And with 25% of the population living in poverty, the access to these irrigation systems is actually quite limited. So the purpose for our project is to provide an autonomous irrigation system for farms, and with this, agriculturalists will have the means to effectively utilize water in cultivation. This is a high-level overview diagram of our system, where it's supposed to be. Here's the enclosure. Down here are the probes that will measure soil moisture. Here are motorized valves, which are attached over here to a water tank. The water tank is provided by our client. Another thing to point out, the sensors, they're 30 centimeters and 10 centimeters, all for different root lengths. The 30 centimeters for larger plants, and then the 10 centimeters for smaller ones. And as you can see, our system is functioning at night, and this is because in order to minimize water evaporation, we are going to be working specifically at night. This is an in-depth overview diagram of our enclosure. So over here, as you can see, we have a rainproof vent, an LCD screen, and a waterproof keypad. Our system is going to be outside, so we have to take care of those sorts of things. And inside of the enclosure, this is sort of an in-depth view of all the electronics that are inside, and we will be talking about that pretty soon. So, important thing to mention, this is a continuation project. The biggest problem that this project was facing is that it was not robust enough. They suffered from poor probe designs, meaning they had inconsistent spacing, leading to inconsistent data, and also just a lack of readings overall. There were poor quality enclosures, which were actually made out of plastic and would suffer from heating up super easily, and you know how electronics are, they heat up as well. So, and they were not waterproof or bug-proof, leading for a lot of problems. In addition to that, they were using the ESP32 microcontroller, not a bad microcontroller, however, it was not power efficient enough for what we needed it to be, and in addition to that, its temperature range was not ideal. Our current design that we're going to showcase today is extremely robust, including the probes and the enclosure. The probes are made with a polyethylene spacing, they're stainless steel to prevent corrosion, have consistent testing for readings. Our enclosure is made out of cement stucco, essentially building material for houses. They have insulation and measurements. And our microcontroller is the 18-mega 328P, which is very, very resistant to a lot of things. And we'll be talking about that pretty soon. So, what are our customer specifications? So, our customer had a couple things. The first thing is this drip irrigation system has to function and sense moisture level and provide water as needed to minimize water evaporation. It needs to have two modes, autonomous and selectable. Autonomous is just supposed to read in the moisture levels and water accordingly without doing anything. And then selectable mode is supposed to retrieve data on the temperature, moisture, and humidity. Since it's an agronomical institute, they want to collect some data. It's supposed to deliver 400 liters per hour of water, open loop. It's supposed to be weather resistant, corrosion resistant, and insect resistant, as I just mentioned. It needs to have Arduino capabilities. In this university, they want to tinker with this product, so they are mostly focusing with Arduino. Our device will come with an owner's manual, needs to be in both English and Spanish. This is due to the fact that Nicaragua's main language is Spanish. And then it needs to check for moisture every 3 hours between 6 p.m. and 6 a.m. Now, enough of this, let's go on to our functionality, starting with the main electronics.
All right, the main electronics, here we go. So here is the overall schematic for the main electronics. I know there's a lot going on, and you're not really meant to look at every single pin and what it's connected to, but it's just to show that although from an overview it might seem like a fairly simple sort of design, there's a lot of different components that have to interface and interact with each other. So this is kind of what we were working through this semester. Starting off with the power components, as was shown in the overview diagram, the power from the system is meant to come from the wall outlet. So we have 120 volts RMS at 60 hertz coming from there, going down to our AC to DC switching supply. This will convert the 120 volts down to 12 volts at 3.3 amps DC. This was chosen specifically because it's also a very common battery type. So in case they're at a rural farm where there isn't ready access to electricity via the outlets, they can also use battery to power the system. The 12 volts will also power our valves, which we'll showcase a little bit later. And then further downstream, we have our buck converter, which basically just takes the 12 volts DC and converts it down to 5 volts for power to our microcontroller and other small components. One of the first real big problems that we ran into while doing this design was that whenever we connected our relay modules to our microcontroller pins, the microcontroller was essentially getting loaded down by the relay module. So basically, to address this, we went ahead and added a buffer stage, which features a common collector configuration of the BJT, also sometimes called an emitter follower. And we also included a protection diode. So whenever the BJT switches off, that change in current leads to a really large voltage spike at the emitter terminal. And basically this protection diode, once that negative voltage comes, it'll become forward bias and give an easier path to ground. As was discussed with one of the specs, we want to collect temperature and humidity data. And for this, we went with the SHTC3 module, which features the SI7021 chip. And this will be communicating with the microcontroller via I2C. And the error tolerances are listed below. And to verify these tolerances, we went ahead and compared it to a digital thermometer, which has relatively similar error tolerances. Here's a table of some readings that we got, and essentially our conclusion was this was within the customer's spec, and we were able to collect and retrieve this data. Moving on to the valves, as Adriana mentioned, we wanted 400 liters per hour open loop in the system. So using let me back up. Our customer has basically described different farms where the vertical height of the water tank slightly differs. So we're designing for anywhere between 2 to 7 meters. And based on some of the specs on flow rate of the valves that we got from the data sheet, we were able to come up with this graph. And as you can see, for 2 to 7 meters and actually quite a bit longer, we were more than capable of supplying 400 liters per hour. Finally, all of this had to be assembled. This was not trivial. The perf board took forever, and a lot of troubleshooting was done to make sure everything was working correctly. Something that was a common issue with some of the past projects is that they would ship the box out and it would arrive in Nicaragua and there would be one wire missing. No one knows where the wire goes. So in order to combat that, we essentially have labeled all of our wires and where the connections are, as well as included a very defined diagram in our owner's manual.
That leads into the software functionality of this project. they're starting with the state diagram. So when you start it up, you plug it into the wall, the system will initialize all the variables and the functions. And then it will ask the user to input the time. This is to calibrate the real-time clock. We'll go into detail for that later. And once it has the time, it'll go into autonomous mode automatically, directly. And in autonomous mode, it will check the time of day. As we said earlier, this system will be active during nighttime. So between the time of 6 p.m. and 6 a.m. of the next day, the system will be active in autonomous mode. Between 6 a.m. and 6 p.m. of the same day, it will be idle or in sleep mode. So if it checks the time and it's in sleep mode, it'll be idle. It won't take any measurements of soil moisture or anything. When it is nighttime in awake mode, it will take the soil moisture. It will measure the soil moisture via ADC. And as you said earlier, this will happen every 3 hours. So it'll happen at 6 p.m., 9 p.m., midnight, and 3 a.m. And then it'll go into watering mode, which is to say that it measures the soil moisture and determines that the plants need watering. And the stars is where the user can trigger selectable mode, which we'll also go into detail a little bit. So this is the user interface. The user will be able to calibrate the real-time clock via a keypad and receive feedback through the LCD. And the guided menu helps the user make sure they get it right. For example, for month, when they set the month, if they enter 13 by accident, the system will correct the user and ask them to enter a valid month, a valid date, and a valid time. And although the system was obviously designed for you to put in the correct time input, if the user wants to kind of tinker and experiment with the system, they can input a later time. For example, if it's 10 a.m., they don't have to wait till 6 p.m. to actually see it work. They can just input 6 p.m. and see how the system operates. So in conclusion, the system has both autonomous and selectable mode. One of the main deliverables of this project is that it responds in real time. So it doesn't just, it's not a sprinkler system that's based on a timer. No, it operates and behaves according to the environmental needs. So like I said, during nighttime, it is idle. Sorry, during daytime it is idle. During nighttime, the system will enter autonomous mode where it will measure the soil moisture content and determine whether it's appropriate to water or when it's not. And finally, selectable mode, which is just data acquisition. The user will be able to press a light chain LED button on the side, which will push the system into selectable mode. And selectable mode will collect data such as the time, the temperature, humidity, and ADC, which corresponds to the soil moisture content, and transmit it via Bluetooth to the user. And this is a demonstration of how the information will look, how it will work. So when they connect to it, the system will tell the user to select the side button if they want to receive data, and that is how the user receives data for the 10 centimeter, for the 30 centimeter. That is the corresponding ADC, the voltage that is being read across the probes in the soil, the date, time, and temperature and humidity.
Moving on to the soil moisture sensors. Here we can see our current design and the previous teams. We can see that the previous teams was not scratch resistant, so we decided to use a heat shrink tubing instead. And we also switched from galvanized steel to stainless because the previous ones had already begun to rust. We also applied a plastic spacer because one issue that we saw that was when they were inserted into the ground, the probes tended to spread apart. And we also added a PVC enclosure on top because one issue that our client had was that the farmers would actually use their foot to stomp them into the ground, and that tended to break things. And so we added that to protect equipment. This is just a general overview of how they work. Our microcontroller will be supplying 5 volts. Our sensors will be acting as a variable resistor. So as the soil becomes more dry, this resistance value increases. We also needed a sense resistor with a known resistance value so we could measure this. Our ADC from our microcontroller will actually be measuring the voltage across this sense resistor. Here we can see our test data. It doesn't show up that great, but we have 4 different areas. We have at the top saturation, below that we have field capacity, the stress point, and then permanent low point. Our main focus will be on the field capacity, which is the optimal level for plant growth. So if we are above this value, our valves will actually close, and if we're below it, our valves will open to allow watering. Here we also did the same thing with the 30 centimeter sensors. The reason why we have 2 types is because our customer really wanted to be able to accommodate for plants with different root depths. And the main difference here is that, of course, since they're longer, it's gonna take a lot longer for the water to reach the sensors.
Alright, now let's move on to the enclosure for our project. This is basically a large view of our enclosure. It's made out of fiber cement stucco, which is basically building siding. So that in itself makes it very weather resistant. Here are the dimensions and the weight. And this is of course designed to be to comply to NEMA standards, making it a type 4 system, which essentially just means that it can be sprayed down and hosed down without anything going wrong internally. And then next, we're gonna go over all the augmentations that we made on the enclosure for the semester. Over here on the left side of the box, you can see the plexiglass cover over the LCD screen. The LCD screen is not weather resistant, and the plexiglass helps with any moisture, preventing it from getting into the LCD screen, and also UV rays, because UV rays can damage the LCD screen over time. Next, you can see the waterproof keypad, of course, does not need a cover. And then on the right side of the box, you can see the autonomous and selectable mode button, toggle button on the bottom. Next, you can see the valves, the A and D valves that we're using, those 2 cable runs, as well as the probe cable runs, which are the 10 centimeter and 30 centimeters. And those cables run about 3 meters long. And then next, we're gonna look at the top and bottom of our enclosure. Here, starting with the bottom, you can see the latch that we can open and close in case anyone wants to access the internal components. And then under that, you can see the 12-volt cable run. And then on the top of the box, finally, you can see the wall-mountable hooks. And of course, while they look small, they can hold up to 125 pounds. So this definitely meets our spec. And then with all of this, we can see that with the augmentations, our enclosure completely meets our customer specifications. And then finally, here's some temperature data that we took, some final temperature data with all of our components inside. While we realize it is gonna be much hotter in Nicaragua, the important takeaway from this graph here is the middle part of day where it is the hottest. So from about 11 a.m. to 3 p.m., our internal temperatures remain much lower than our external temperatures. And that number increases as temperatures get hotter. So here we measured 5.38 degrees Celsius cooler internally than externally. And this was measured using that digital thermometer with about a 0.5% degrees Celsius tolerance. And then finally, we're gonna go over a quick video here. This is just a quick water test. So basically, our customer wanted to make sure that can it be sprayed down? Is it gonna be safe? Are all the internal products gonna be safe after being sprayed down? So this is very extreme. This could also be seen as like rain. And then after this, here is our dry test. So we had a paper towel inside, and as you can see, everything remains completely dry. System remains operational. And with this, our enclosure is indeed a Type 4 system.
Alrighty then, so now we're going to do a prototype demo. Let's go over here.
Project for Senior Design 2. First, we will get started with our user interface, where the user will have to go through the menu in order to input the year, the month, and the day. Here, we inputted the year 2024, the month 7, and day 7, just as purely random values. However, in the hour, minute, and second, we inputted hour 17, minute 59, and second 45. This is so we can showcase sleep mode briefly working, and then autonomous mode going out, which is supposed to go out in hour 18. As one can see here, this is how it looks. Now, we went ahead and have the Bluetooth module turned on and connected to the computer. You will see throughout this video how we showcase how these things work in conjunction together. Here, on the left-hand side, one can see the 30 centimeter probes, and in the right-hand side, you can see the 10 centimeter probes, along with their corresponding valve. Along to this, you can see in the right-hand corner, the Bluetooth serial device. Now, in this clip, you will see that we will receive the first measurements of what the probes are reading, and then the valves will switch on. The first measurements are less than the indicated value for soil moisture, therefore the valves will turn on, which means a successful first test here. Now, we will manually insert some water in order to depict the watering event that in a real scenario will be in drip. The first sensor to detect soil moisture is the 30 centimeter sensor, as one can see, and the Bluetooth module on the right, and as you can see, the valve at the left is closing. Let's continue on and see what happens next.
The video is now currently sped up, but I'm going to go ahead and put it over here. As it takes a while.
As one can see, this section has been sped up, and that's because the water for the 10 centimeter probes took a longer time to get to the bottom. But as one can see, the values have been slowly updating themselves through the Bluetooth module. Now, here, it will reach the soil moisture and the valve will close for the 10 centimeter probe. This is a successful run of our testing, and we're happy and thankful that you got to see it. Thank you.
So, let's go on to our conclusion. So, as you can see, our system successfully switched between autonomous and selectable mode. Our system sensed the soil moisture and was able to minimize water evaporation. System is robust and resistant to several external factors. And now, since we were able to present early, our team really wants to collect more data to further determine and measure the accuracy and precision of the system. So what did we learn? We learned a lot about debugging. So essentially in our scheduling, when I made the schedule, I told the team, okay, November, we have it entirely as a float month. So we're like essentially allowed to like do whatever if we need to. And we definitely needed November. We so needed November. So definitely we learned a lot about that. Teamwork especially. I have to tell you guys, this team is the best team I've ever worked with. They are hardworking and great problem solvers, which is an amazing quality to have in a team. We had a lot of communication between each other. We were constantly communicating each other on results and things that needed to happen. And documentation. If you didn't document it, it really didn't happen. And that was very true for certain scenarios. So we learned all this. Any questions?
So, I've seen earlier versions of this, and, one of the real failure points was the sensors. And I'm, really, impressed with the simplicity and ruggedness of your sensors. That's wonderful. Have you been through a process where you're calibrating, like a moisture sensor?
So essentially, the testing that Maggie was doing was because our client, he noticed that the calibration part was very complicated, especially if you're adjusting from loam soil in Houston to soil in Nicaragua. So he was just like, hey, calibrate it, just manually, like almost hard code it into the code. That's why he wanted Arduino capabilities, so he could go and tamper it himself. But do it just for loam soil in Houston. That was what the client was. Yes, sir.
Yeah, first of all, we have seen this project many times, but this is the first time that we actually see an explanation of how you guys have tackled improvements and what they are, so I wanna commend you for doing that. You mentioned that you were asked to document in English and Spanish.
Yes, sir.
What about the actual display? You guys consider having that display in Spanish, right?
Yes.
The operators, I assume, are farmers, right?
Yes, definitely. So John Wise, our client, he oftentimes stated to us that he would go and set it up for the farmers, and then would like leave it in autonomous mode, which is the goal. But we did discuss at one point with the software section, I was like, hey, I can make you the Spanish part if time allows it. And unfortunately, time did not allow it. But yes, it was something that we wanted to do.
So a couple of points. I'd seen the project, but I'd forgotten that in your design specification, you didn't mention anything about connectivity, and then at the end I saw Bluetooth. And that kind of confused me in saying, well, wait, how do you measure this, how do you, manage it? Because what I did hear from you is exactly how this fleet of things, in a farm is actually managed. How do you collect the data, how do you debug it, and how do you actually see that something's wrong, and what is the telemetry? You also didn't mention anything about the telemetry, so I'm wondering that there is an automated system for some level of telemetry collection, which will also be usable for a debugging perspective, seeing if something's wrong and something's not working, that somebody needs to go pay attention. And I don't know if there were alarm systems or something else to say, oh, this is not working. So I didn't hear anything back. I'm wondering, all of that's done through Bluetooth, which is not possible because then it's a closed range system. So can you elaborate on what those things are? I know I've put a bunch of those things, but I was just confused as to where the connectivity is stuff is.
So definitely, we can explain that. So our client, he specifically asked it just to deliver Bluetooth data, and if he's close to it, he just wants to have it himself, and that he wanted to experiment with the system after that. That was the goal of it. He really didn't want any signals, anything. That was his goal with it, essentially. Just tinker with the project.
He's very much a tinkerer, so I think he just wants to kind of play
Hopefully he
around.
doesn't have a very large farm.
There actually, we have,
We have pictures of this farm.
I'm just saying.
There it is.
it's not.
Okay, well then, yeah.
So I guess the point that he's making is like, maybe you have to clarify, your sensors are not connected to Bluetooth. Your sensors
No.
are connected, they're wired. The Bluetooth is just like if there is anything that the farmer wants to collect as data for him to keep, he will go close,
Now,
right?
that makes sense now. It's just that you didn't mention anything about the connectivity in your design specification or anything, so I was like, well, okay, but then you said Bluetooth, and I think, well, where did that come from? And how, what is it attached to?
Yes, yes. He only requested for it to be able to collect data. So there were two choices we had, SD card or Bluetooth. So we went ahead with Bluetooth in this round.
And unfortunately, because I have to ask a security question, then once you have this Bluetooth thing, then what do you do? Because it's a little too easy to hack,
Yes.
stuff that.
Yeah, I recognize that that is definitely a risk in the project that we have to acknowledge in our owner's manual, that essentially it is a security risk. So, yeah.
First time I've seen this, so great job. Thank you for showcasing this. As you worked on this project, you had a set of guidelines, specifications to meet, right? You guys collectively as a team think about, hey, what are the limitations of this system, and then how would you maybe make a 2.0 system if you had to?
Yeah, if we had to make 2.0, one of the things we discussed is that the sensors would be Bluetooth as well. So that you could place like several of those sensors in a row, and they would relay back to the box and be like, hey, this is what's going on in this one and this one. Teammates, are there any other improvements you would make?
I would say for the electronics, we ideally would have liked to have gone with the PCB board. But just for the sake of time, none of us knew any EDA software, so we were like, okay, we'll just solder everything on. Initially, we did have some problems with like just components, just a little loose and stuff, and we mitigated that as much as we could. So we have a bunch of Velcro connections to make sure everything stays down and like stays on the board. But ideally, like you could probably reduce the size of the board pretty significantly with a nice PCB board.
I think also for increased reliability, you mentioned earlier, I think, I don't know, I'm not sure who mentioned it, but the battery backup, right?
Yes. Yeah.
You'll have AC as the normal source of power, but if y'all can have a set of batteries.
Right, yeah, so there is an option, if they're in a farm somewhere, they also, we've spec'd it out to fit a very common battery size, so
Good.
they can also use that straight DC power.
Oh, great presentation, by the way, because it's good to see each one of y'all assigned to a different area and then working collectively together to achieve a common goal, so that was good. Did have one clarification, y'all mentioned the enclosure, was it corrosion resistant?
Yes, that specific material, I chose that just because of the corrosion resistance, as well as, it's cement, fiber cement stucco, so, we won't have to worry about, any water getting in and of course corrosion.
Yeah, cause I saw you reference NEMA.
Yes.
So it wasn't a NEMA 4X enclosure, cause that's corrosion resistant versus a NEMA
Yes.
4 enclosure, which is not corrosion resistant. I think I saw that somewhere in one of the
Yes.
slides.
We wanted to be able to kind of mold the system as we needed to, and we saw
Okay.
those NEMA enclosures and we just felt like
there we go.
we needed more availability. So that's why we designed the enclosure ourselves.
Okay.
Yeah, and the main reason we went for that is because our client says, what if a farmer splashes it down? And we were all like, why would that happen? But yeah.
That's good.
First of all, great presentation. I thought it was really good. A couple of questions though. One on the data acquisition. You have Bluetooth. Is that just live data, or is there any kind of caching of the data so that you can retrieve historical data? Say you aren't there whenever a specific event that you're interested in.
Yeah, it's just live data. So if the user wants to collect data, they select the code and each state either receives it, unselects it, and collects it.
So a 2.0.
Yeah,
2.0.
yeah.
Second, are you concerned at all about overshooting your target for moisture? Because you're turning on your valve, and I don't remember, or I don't know if you talked about what kind of actuation you have on these valves. Is it proportional or is it just bang bang? But I mean, if you start unloading all of this water on the soil, it takes time for that to reach down to the probes. By that time, have you noticed that you're actually overshooting? And what would your mitigation plan be if you had your?
So that's the wonderful thing about drip irrigation, really. Drip irrigation happens so slowly, and our sensors are quite sensitive and like take a bit of time also to send it back to the enclosure. So that slow movement, I think, is like even ideal for what we're doing.
And we also only water on the hour. So for all of 6 p.m. we water, and it waits 2 hours for it to settle, and then measures again at 9 p.m. And then again at midnight, and again at 3.
Yeah, so it's like a fail-safe. We would never water for more than an hour, essentially.
So you haven't noticed that overshoot in any of your testing, and that's not a concern.
For the most part, no.
Yeah, no, not so.
So, you showed a diode that you placed in your driver circuit to protect it.
Sure.
How did you know to put that on there?
It's very common for any type of inductive load.
So one of the first projects I did when I got out of school was driving a relay, and I didn't put that diode on there, and it was driven by a one-shot, and so it was the ultimate one-shot. My boss told me what an idiot I was and said, put a diode across it, and so you've already learned a valuable lesson.
So a comment and a question. The comment is that I think several things came together here. One is that we were finally able to break through to John Wiss and get a decent set of product specifications for this, and which has been a real challenge in the past. And second, so pointing out the importance of having a sponsor or a mentor or a client who will give you real specifications that don't change every time you talk to them. And the second component here is that this is an amazing team, that they go way beyond what other teams do to dig down to the bottom of what's going on. Most teams will not do that, or they don't know how. So congratulations on that. I don't see how you could possibly earn anything less than a C- for that. And then the question is, were you nervous about taking a completed working project and spraying it with a water hose?
We were, it was actually yesterday, we practiced in front of Dr. Brett and Dr. Grassi, and they were like, you know what would be great if you guys showed if it was waterproof, and we all stared at each other like, yeah, that would be awesome. And so we made the very risky decision to go ahead and do it yesterday, but I had full confidence.
We had complete faith that it would work.
95%
Does it still work?
It does.
still work.
Yes, I can confirm. I tested it this morning.
And if y'all wanted to see it, it's at the lab. We could always walk anyone over there and actually like showcase it to you.
Can we spray it down with water again?
While it's in the lab.
And I just wanted to mention, Pepe pointed out to me that Lane has been a mentor for this project for many semesters. And we were very happy that they finally succeeded. You know, now in view of Lane's retirement, he can say that he retired in.
So I didn't do that much with this team. I met with them occasionally and helped, I guess, channel them, but Doug Barrett really spent a lot of time with him and, was instrumental in the interaction with John Wiss, and the team, so, kudos to Doug for all of that. And it was Doug that, you were the one who suggested this project in the first place years ago, yeah.
And connected them with Bionica.
Yeah, right.
That's the benefits of being an IEEE. I'm a believer in a national organization, so exercise your network, right, to make the connection that you need to make.
Okay, well, that was absolutely awesome. Thank you guys.
Thank you guys.